Welcome, dynamics students. In this lecture, we'll be applying Euler's first law so that we can use the center of mass of bodies to track their motion and apply Newton's laws of motion to bodies treated as points at their center of mass. So this will feel an awful lot like a review of some basic physics for those of you who have taken that recently. And we'll also be pulling in a lot of basic concepts from statics, equilibrium where that's appropriate. So this may seem like a review of those concepts for those of you who've just taken those courses, and a recap maybe for those who haven't. So just to review why we can do this, if we focus on a body's center of mass, we can apply Newton's second law and calculate the body's motion. Translational motion, I should add. This is something that Euler's law allowed us to do. And I have another video where I went through the proof of why that was possible, but we're just going to put that to work now. So we can say that the sum of the forces is equal to the mass times the acceleration of the center of mass point, which is also equal to the mass times the time derivative of the center of mass's velocity, second derivative of its position. So this is leaving off force, this is pretty familiar kinematics, rectilinear kinematics expressions, which you should be familiar with. But this time we're going to solve for the acceleration of the center of mass by finding some force resultant. So we're going to start with a pretty easy force resultant. So we have we want to know the trajectory of a body's center of mass that was launched into the air. So we're given an initial velocity and launch angle to the horizontal, and it looks kind of like a point, but in this case, this really is. This could be it could be a car, it could be a cow, it could be something. It could be a satellite, something big. But because we're only looking at its motion, rectilinear or curvilinear, we're not looking at any rotation, we can treat it as a point at its center of mass. So let's see, what forces do we have acting on it? Force resultant is negative mg in the j-hat direction in this coordinate system. It's subject only to gravity. So we can say that its mass times the second time derivative of its position at any time is equal to m times its x position, first time or second time derivative in the I-hat direction, plus second time derivative of the magnitude of its position in the j-hat direction, so yj-hat. So if we want to we'll relate that to our acceleration from our force, so we're going to apply Newton's laws here before we go diving into all the integration of the kinematics. So what we really need is an expression that has only acceleration. So it's something so simple it's easy to forget that. Our acceleration, our double dot OC, and each dot indicates a time derivative. So ROC is the second time derivative of the center of mass C with respect to the origin O here. So this is otherwise known as the vector acceleration of the center of mass. Is again our second time derivatives of our x and y positions in the respective directions. Right hand positive for I hat and upward positive for j hat is equal to 0 in the I-hat direction. We have no forces acting in the I-hat direction, and so we have no acceleration in the I-hat direction, minus g, which is our acceleration in the j-hat direction, because our force resultant was mg, and if we divide by m, we're left with just g, and that's in the negative direction. So we can get our first time derivative position, otherwise known as velocity, of the center of mass by integrating once, and so that just gives us v sub x, whatever velocity in the x direction, plus v sub y, velocity in the y direction, and we know that v sub x is constant and equal to our initial velocity times cosine of our launch angle. Use a little bit of trig there, so that's v sub x and it stays constant, and v sub y will be the same, plus the contribution from our acceleration. So we'll do an integral for that. So v sub y is the integral with respect to time of our y acceleration, which is negative g. There's a little negative sign there. So that's negative gt plus c. And here's where we pull in that initial condition of v sub y, v sub 0 sine theta. So first initial condition. One initial condition per integral per direction is what you'll need to get your full equations of motion. So now our full velocity expression would be v sub 0 cosine theta plus v sub 0 sine theta minus gt, which we have down here with their proper unit vector directions. Okay, so if we want position at any time, we just integrate again with respect to time. And so we end up with our x position at any time as v sub 0 cosine theta t in the I hat direction, and then our position at any time in the j hat direction, y, is going to be our y velocity expression here, integrated with respect to time. So we're going to end up with 1/2 t squared times negative g times t times our initial velocity expression in the y hat, and then we're going to kick out another constant of integration in both directions, which would be our initial position in the x and y, which, given that it started at the origin, is 0 in both cases. So if we put together this expression, a little pen here. If we put together this expression for acceleration, this expression for velocity at any time, all time dependent, and these two expressions for position, these would constitute our full equations of motion. So anything we needed to know about where that body was, or where that body's center of mass was, because that's all we really know, where that body's center of mass was at any time, we can find it with these three expressions. So for example, if you wanted to know the apogee of the trajectory, the high point that it got to, the highest point it got to before it started going down again, y max, we can look at the maximum of this y function. So we can take the first time derivative of this, see where it equals 0, and find the time associated with that max height. Oh, well, we conveniently already have the first time derivative in our velocity expression, so we can just see where that equals 0. So we know that's set this here equal to 0, and solve for t. So our max height is at a time of v sub 0 initial velocity sine theta over g, gravitational acceleration. So if we want to know how high that actually was, we plug this expression in for t into our expression for height and solve. And so we can get that expression, which ends up being, I'll get rid of some of these lines. Our expression for maximum height ends up being this, initial velocity squared sine theta over g, and again we got that just by plugging the time of max height into our expression for height position. And then we can find the corresponding x by plugging the same height, same time of max height into the x expression and find the x position when the y position was at max height. We can also go one further and say what is the x position where it actually lands. So we can set y equals 0 because it lands on the ground at y equals 0. So we can set y equals 0, find that time, plug it back into x, and get the x position that corresponds to max total distance, x max. And we get this. So it's just some algebra going back and forth. Once we have our equations of motion, really we can tell anything we want to know about the motion. So that was a very simple example that had such a simple Newton's second law that I almost forgot to to apply it. But it was a very important step that in this case we couldn't just jump to assuming g is a gravitational acceleration. It was really important to say the force resultant was weight only, which is mg, and then the acceleration is weight divided by mass, which is g. So let's go to something where we can't quite take Newton's second law for granted. So we have something that has multiple forces on it. We've got a 20 kilogram block sliding, down a ramp, and it's got some kind of corner where our origin is. So we are measuring our x direction down ramp. So as we slide down the ramp, our x is getting bigger and bigger. And we're given a coefficient of kinetic and static friction. So for those of you who haven't worked with friction for a while, if a body is stationary, it's not moving, to get it moving, you equate max frictional force at imminent slip to normal force times the static friction. If a body's already moving and you're looking at the frictional force necessary to continue that motion, you look at the mu sub k, coefficient of kinetic friction. Kinetics always less than static. So anytime we're looking at onset of motion or something needing to move or not being moving originally, we use mu sub s. Most of our dynamic problems will just use mu sub k, and in fact quite often you'll be given a mu for something that is stated as being moving, that it's not starting from rest. You can just assume that it's mu sub k. All right, so the body is released from rest. So it had to overcome mu sub s to get moving if it's moving. And someone wants to know, what is its speed after it's 5 meters down the plane? So they want to know a velocity at a position. We need an equation of motion to tell us that. But to get that equation of motion, we need to use Newton's second law to relate force resultants in all the directions it could be moving to acceleration. And then once we have acceleration, we're off and running. Ha, pun intended. Okay, so let's apply some statics. And our first step in any dynamics problem, so this is common to statics, we're going to use an FBD. So again, anyone who's just taken statics and you thought you'd seen the last of FBDs, think again. They are your friends. So here's an FBD of the block, and I'm drawing the entire FBD, but because I'm approximating this whole block as simply a point at its center of mass. The box is a courtesy just to get my vectors going in the right direction. Really, I'm treating this as a particle. If I suddenly find myself doing a radius or looking at a moment, I can no longer look at that as a single particle. So just focus on the center of mass, which I'm assuming is right up in the middle. So I've got weight in the downward direction. I have a normal force coming from the ramp, normal to the ramp, and then I have frictional force acting opposite the direction that I know it's sliding. I've been told it's 5 meters down the plane. I figure it slid down the plane, so friction is always applied opposite the direction of motion or imminent motion, so friction is pointing back up the plane. So I can resolve my mg vector into a component parallel to my x-axis and perpendicular. And I'm going to do pretty much what I did in statics, which is write equations of force equivalence. We call them equations of equilibrium in each orthogonal direction. Well, things aren't going to be in equilibrium, so I can't call them equations of equilibrium, but I am going to apply Newton's second law in each orthogonal direction. So if I do that in the y direction, I actually am applying an equation of equilibrium. The box is not flying off the ramp and it's not sinking down into the ramp. It actually has zero acceleration in the j direction. So I am at equilibrium in that direction, so I can say that the normal force is equal to mg cosine theta. And having normal force and knowing that I'm moving when I'm doing my equations of motion, I can use mu k, which gives me the frictional force, an expression for frictional force as a function of mu k, g, mass of the block, and the angle of tilt of the slope. So now I turn my attention to a direction parallel to the slope. So I can write equations of acceleration parallel to the slope. So I know the sum of my forces in the x direction is going to equal the mass times some acceleration in the positive direction I hat, which is downslope, because I've defined positive downslope. So what do I have? I have pulling me down the slope. So here's our tally of forces. From my FBD, I have mg sine theta, basically pulling me down slope, and I have frictional force, which I have already determined to be this, pulling me up slope. So my F resultant is just this. So force is parallel to the ramp, and I can factor out an mg and make this a little simpler expression and point it in the right unit vector direction. So this is equal to, by Newton's second law, this is equal to ma in the I hat direction. So I'm going to collect terms in orthogonal directions, which is one orthogonal direction I'm concerned with. So I'm going to write the sum of the forces in the I hat direction equals mass times the acceleration in the I hat direction. And I have canceled mass in both of these, and then gotten an expression for acceleration in the I hat direction is just this term. And none of these terms are time dependent. So I can integrate with respect to time very easily by treating this whole thing as a constant, which I did. So I have this whole expression times a constant. It equals my velocity at any time, because my coefficient in my constant of integration was 0 because it started from rest. V0 is 0 since the block starts at rest. If I want the position at any time, I do the same thing. Integrate again, and so I just throw out a 1/2. I have a t squared. I have the same constant expression plus my initial position. And again, we are looking at a 5 meter displacement. We're not concerned this time of exactly where we are relative to our origin. We're told, hey, you went 5 meters from wherever you started. Now, I could say x0 and then say the 5 meters is x0 minus x at any time, which might be better if I'm going to move twice maybe. But I'm going to call that x sub 0, that initial position, 0, because I'm going to look at the time at which x, which I'm going to define as displacement, is 5 meters. That's a little bit simpler. So I can define v as a speed in the I hat direction. V is velocity. It has a vector direction, but because the velocity is only in the I hat, it's actually a speed. And in this case, x, because I made x sub 0, 0, this is now a displacement rather than a position. So I was asked what? Speed for a 5 meter displacement. So I find a when associated with 5 meter displacement. I plug 5 meters in for x. I solve for time. It's 1.17 seconds. Now I plug that time back into my velocity expression. Love those equations of motion. And just crank through the algebra using the values that I was given for phi and mu sub k, 60 degrees and 0.3, and I get 8.5 meters per second. So important points. Start with a schematic. Assign a coordinate system that makes sense for the motion that you have. This is rectilinear, so xy works great. And in this case, I made my motion, I made one of my coordinate axes parallel to my motion. So my motion was defined in terms of that axis. So I have basically 1D motion here. Next step, FBD. Everything, all my motion, my acceleration is going to depend on the force resultant. There is no way I am going to find the force resultant in the directions that I want without an FBD. Do not try it. As important as this was in statics, is probably more important in dynamics, because again, if you don't get that acceleration right, all your equations of motion will be wrong. So very important. I also got a very critical piece of information that helped me solve for an unknown force vector. By doing my full FBD, I was able to use my equilibrium state in one orthogonal direction to solve for a force that I needed to calculate acceleration in the other. And then I applied Newton's second law, equating mass times acceleration in the orthogonal direction I'm concerned with the force resultants in that direction that I picked off my FBD, and then cancel out masses. I isolate my expression for acceleration. Then all I have to do is integrate and drop in initial conditions, and I have all the equations of motion that I need. So we have a couple of more examples coming up. I'm going to carry forward with those in another lecture, but we're going to use, you get a little glimpse here, we're going to use our curvilinear, normal, tangent and cylindrical coordinates to solve another problem or two, and show cases where those two actually can be interchanged in some cases. So stay tuned.